What specific problem does the self-taught reasoner, STAR method, seek to address in the realm of reasoning capabilities for LLMs, and how does it differ from existing methods?
The self-taught reasoner, STAR method, addresses the limitation of existing models that cannot improve on examples they initially fail to solve, particularly in generating and refining rationales for complex reasoning tasks. Unlike traditional methods that require access to strong or ground truth rationales, STAR employs an iterative bootstrapping approach, allowing models to generate their own rationales and answers from a dataset of questions and corresponding answers. This process involves filtering generated data to retain only those rationales that lead to correct answers, thus creating a bootstrap dataset for further training. Additionally, STAR introduces a backward reasoning process called rationalization, where the model generates new rationales based on correct answers provided as hints, enhancing its reasoning capabilities. This self-bootstrapping mechanism differentiates STAR from existing methods that rely on external supervision or strong models for rationale generation.
Can you explain how the STAR method works, detailing the iterative bootstrapping process involved in rationale generation and the post-rationalization approach step by step?
The self-taught reasoner, STAR method, employs an iterative bootstrapping process for rationale generation, starting with a dataset of questions and answers, where strong rationales are not required. Initially, the model generates a rationale and an answer for each question, filtering the outputs to retain only those rationales that lead to correct answers, thus creating a bootstrap dataset of questions, rationales, and answers. This dataset is then used for supervised fine-tuning to improve the model's performance. To address the limitation of not improving on initially incorrect examples, STAR introduces a post-rationalization approach, where for prompts with incorrect rationales, the correct answer is provided as a hint, allowing the model to generate a new rationale based on this correct answer. This synthetic data from the post-rationalization process is incorporated back into the STAR training objective, enhancing the model's reasoning capabilities iteratively.
Using a hypothetical example, can you illustrate how the STAR method generates rationales and uses them to improve the performance of a language model?
The self-taught reasoner, STAR method, generates rationales through an iterative bootstrapping process. For instance, consider a dataset of questions requiring strong reasoning, where a model is prompted to produce an answer and a rationale. If the model generates a correct answer, the corresponding rationale is retained, forming a new dataset, D_text star, that includes the questions, the generated rationales, and the correct answers. This dataset is then used to train the model with a supervised fine-tuning objective, enhancing its reasoning capabilities. Additionally, if the model initially produces an incorrect answer, STAR employs a backward reasoning process where the correct answer is provided as a hint, prompting the model to generate a new rationale, thereby refining its reasoning skills and improving overall performance.
What are the primary theoretical or practical advantages of utilizing STAR over traditional supervised fine-tuning methods?
The primary advantages of utilizing the self-taught reasoner, STAR, over traditional supervised fine-tuning, SFT methods include its iterative bootstrapping approach, which enhances the reasoning capabilities of language models without requiring access to strong or ground truth rationales. STAR allows models to generate and refine rationales based on their own outputs, creating a dataset of questions, rationales, and answers that can be used for further training. Additionally, STAR incorporates a backward reasoning process through post-rationalization, enabling the model to improve on previously incorrect responses by generating new rationales based on correct answers. This self-bootstrapping mechanism leads to better generalization and performance, particularly in reasoning tasks, as evidenced by the STAR DPO model outperforming traditional models in various evaluations. Overall, STAR's ability to leverage its own generated data for continuous improvement represents a significant advancement over the static nature of traditional SFT methods.
What specific methods were employed to validate the performance of STAR, and what datasets were used during testing?
The performance of the self-taught reasoner, STAR, was validated through experiments using two primary datasets, ultrafeedback and ultrainteract. Ultrafeedback is a large-scale feedback dataset containing 61,000 pairs focused on general instruction following, while ultrainteract consists of multi-turn reasoning trees that emphasize math, code, and logic tasks. The evaluation involved comparing the STAR DPO model against classical reward models like Bradley-Terry and pair RM, as well as zero-shot RLAIF evaluations across various categories in the reward bench benchmark. Additionally, the experiments assessed the model's performance on reasoning tasks specifically, highlighting the STAR DPO model's superior generalization capabilities. The results indicated that STAR DPO achieved the best performance on both in-distribution and out-of-distribution tasks, particularly excelling in the safety category of reward bench.
How do the results of the STAR method compare to classical reward models in terms of accuracy and generalization, particularly in out-of-distribution tasks?
The results of the STAR method, particularly the STAR DPO model, demonstrate superior performance compared to classical reward models in terms of accuracy and generalization, especially in out-of-distribution tasks. In the experiments, the STAR DPO model achieved an in-distribution accuracy of 73.9%, matching the performance of classical models like Bradley-Terry and pair RM, which had comparable accuracies around 73 to 74%. More notably, in out-of-distribution evaluations on reward bench, the STAR DPO model outperformed both the base model and the trained reward models, achieving an accuracy of 81.9%, while the GenRM model reached 78.9%. Additionally, the STAR DPO model excelled in the safety category with a remarkable accuracy of 91.0%, significantly surpassing the best classical model, pair RM, which scored 81.8%. Overall, the STAR method not only matches classical models in accuracy, but also exhibits stronger generalization capabilities across various evaluation categories.